Okay, 3.3, rational exponents. That means exponents that are in the form of a fraction, m over n. What you are going to do at first is get your calculator out and simply evaluate each of the following. So you notice they're in pairs. You have the square root of 4, and then you have 4 to the power of 1/2. Make sure that when you're doing this 4 to the power of 1/2 on your calculator, you can do it like this. Okay? That way you'll get the right thing. Make sure that your exponent is 1/2. Yes, you need brackets to make sure that the exponent is 1/2. Otherwise, you'll be doing 4 to the power of 1 divided by 2, and that is not what you want to do. Even though in this case it's the same answer. But in the next one it won't be.
It is 2.
Go ahead and do those, fill them in, and then think about your answers. Okay, your page should look like this, and what does that tell us about the expressions? What does that tell you about these expressions, and these expressions, and these expressions?
They're equal.
They're equivalent, 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 equivalent. That means if you get a situation where you have the square root of 4, you can rewrite it as 4 to the power of 1/2. Or if you get a situation where you have 100 to the power of 1/2, you can rewrite it as the square root of 100. Now that's really easy when we're talking about square roots, but this rational exponent doesn't have to be 1/2. Okay? It could be something like 4 to the power of 2/3. Okay? And we're going to figure out what that kind of stuff means as well. Okay, just below that you have a little box, a little table with exponential form, root form, and words. And we're just going to look at 3 different examples. Okay? So if you had, for instance, 8 to the power of 1/3, in root form, that would be the cube root of 8. Okay, so this this symbolism might be new to you, but if you have the square root symbol, which now we just call the root symbol, and you put a 3 on the little shelf there, it now says the cube root of 8. And we'll explain what that means in a second. But in words, it's what I've just been saying. This is the cube root of 8. Okay, what that really means, cube means there's going to be 3 factors, right? If you think about the volume of a cube, it's length times width times height, except on a cube, all the sides and height are exactly the same. They're all x, x, and x. So cube just means you have 3 factors that are exactly the same. And so what we're asking for, if we're finding the cube root of a value, we're saying there is a factor that if you multiply it by itself 3 times, it will be 8. 2 times 2 times 2 is 8. Therefore, the cube root of 8 is 2. 2 is the factor that gets multiplied by itself 3 times to get up to the value of 8. Okay? At any rate, right now, you just need the language and the symbol, the cube root of 8. The next one that we want to think about is 16 to the power of 1/4. How would you write that as a root?
4 and then 16.
Okay, so the radicand, that's the number under the root symbol, is 16. The index is 4, and the whole thing together is called the radical. Okay, the radical. So we're working with radicals. How would we say this? This is the 4th root of 16. Okay, so we're looking for a number that if you multiply it by itself 4 times, you get 16. What is that number? It's 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. Okay? Good. Can we write a general statement for this? Yes, we can write a general statement. If we have an exponent with a base, so we have a power with a base and an exponent, so you have b to the power of 1 over n, you can rewrite that as the nth root of b. The nth root of b. So n is the number of factors, b is the result, and the nth root of b is the number that gets to b after multiplying by itself n times. Okay, we're going to take this concept and apply it to a handful of examples. Okay, example 1, we're asked to evaluate. That means get the numerical answer. There's no variables there. There's no missing information. So go ahead and take what we know and get the answer. Now, there are a couple different ways of doing this. Really, the easiest way to think about this is just to convert it into root form. Okay, 8 to the power of 1/3 is equal to the cube root of 8. That means I'm looking for the value that if I take 3 factors of it, I'll get 8. So something times itself 3 times equals 8. We've already done this one, so you know it's 2. Okay, why?
It's 2 times 2 times 2 is 8.
Yeah, so just because it's our first example, we're going to write that down. Because 2 times 2 times 2 equals 8. And you can even give yourself a little 3 factors. So the cube root of 8 is 2. Second one. In the second one, we're dealing with a negative base. And the exponent is rational. It's 1/5. So we're looking for the 5th root of negative 32.
That's C. B is negative 16.
Either way, let's do this one next. We'll do C first. Okay, so we just have to try to figure out what number multiplied by itself 5 times is going to be 32. So you think, oh boy, that 32 is a pretty big number. Maybe you try, 4 times itself that many times. Well, no, then you get a massive number. Maybe 3 times itself. No, just 2 times itself, right? 2 times 2 is 4, 8, 16, 32. 5 factors of 2 will get us up to 32. But we also have this negative sign out front. Okay? So first we're gonna kind of backtrack, rewrite this as a root. It's the 5th root of negative 32.
But you couldn't have a negative.
You can't have a negative, you can't have the square root of a negative number, because now you know, if you're looking for a square root of something, let's just call it 25, you're looking for the number that if you multiply it by itself, if you have 2 factors, 2 repeated factors, you'll get up to 25. So with 2 factors, you'll only ever get a positive value, because either both of these are positive, and positive times a positive is positive, or both of them are negative, and a negative times a negative is a positive. So that's why you can't have the square root of negative 25. Doesn't exist. Okay? But if you're looking for a cube root of something, now you have 3 factors. So look at what happens if you have negative 2, negative 2, negative 2. Negative 2 times negative 2 is positive 4, but that 3rd factor makes it negative 8.
So the 5.
So you can take the cube root of a negative number. You cannot take the square root of a negative number. Can you take the 4th root of a negative number?
No.
No. Okay? Doesn't exist, not possible. Because now you have 4 factors. 4 factors, whether the factors are positive or negative, will always result in a positive value. So now you're seeing a pattern. If the root is even, like this one and this one, can I have a negative? No. But if the root is odd, meaning I have an odd number of factors, then can I create a negative? Yes.
But I thought you couldn't have a negative under the square root.
This is not a square root. This is a 5th root. Okay?
Oh, yeah.
So
yeah.
we're looking for the value multiplied by itself 5 times. That will result in negative 32, and that value is negative 2. And again, we'll just do a little because here. Negative 2, negative 2, negative 2, negative 2, negative 2 equals negative 32. All right, in your notebook, we're going backwards to B now, and we want to see this. Now, we have a negative sign, and we have a 4th root. And I'm going to tell you that this is still going to work. Why?
Excuse me?
We just explained that if we have an even root, we can't have a negative under the root symbol in the radicand.
Because
But
we'll
now
just
we
make-
do have an even root, and I'm telling you it's still going to work.
Because we'll just make it positive.
Because you put the negative sign 4.
The negative sign is actually outside of the radical symbol here. See how here the negative is part of the base? Here the negative is not part of the base. So this is actually negative the fourth root of 16. What number times itself 4 times is 16? 2. So we're looking at negative 2. Okay?
Interesting.
So unlike here the negative symbol is part of the base. Here it is not. Okay? Here, no matter what you pop out at, no matter what this evaluates to, it's going to be negative. Okay? So the fourth root of 16 is 2. We're looking at negative 2. Okay, so now we have 16 over 81. We have a rational base, and we have a rational exponent. Okay, the first step is going to be, again, rewriting this as a root, as a radical. It's the fourth root of 16 over 81. Now, just like exponents apply to the numerator and the denominator, this fourth root applies to the numerator and the denominator. So for me, I would really think about it. You don't necessarily need to write this in your practice problems, but this is how you're thinking about it.
Yeah, because it applies
Okay.
to both things.
Because it applies to the numerator and the denominator. So now we have the fourth root of 16, which is 2, over the fourth root of 81, which is 3. And again, we could write it out. This is because 2/3 times 2/3 times 2/3 times 2/3 equals 16 over 81. Okay? Okay, example 1e, they do something real nasty. They give you a negative base, and they raise it to a negative rational exponent. Okay? So step 1, what do you think step 1 is going to be?
Put it into that weird form thing.
Put it into radical form?
No.
No.
I will put it in a fraction.
First of all, I want to take the reciprocal so that my exponent is positive. So it's 1 over, my base doesn't change, negative 27, but now I have to the exponent positive 1/3. From here, I can leave my numerator alone and just write my denominator as a root. It's okay that my base is negative because I have an odd root. It's the third root. So what's the third root of 27? 3, and I know it has to be negative. So negative 3 times negative 3 times negative 3 is negative 27. It's going to give me negative 1 over 3. Okay? If you did this first, 1 over negative 3, that's fine. But then go ahead and put that negative sign out in front. We never leave it in the denominator. We'll always put it out front, or in the numerator is okay too. That's nice and clean like this. Okay, if you flick back to your note page, to the first page of this lesson, so I think page 11, you should have some space for more notes. Yeah? So this is one property that we already learned. So if you have a rational expression in the form of 1 over n, rational exponent, 1 over n, you just stick the base under the radical and this becomes the nth root. Notice the denominator of the exponent goes here. Okay? Well, it turns out that the numerator of the exponent actually is out here. Okay? But anything to the power of 1 is just itself. Now we can use that idea to then work with more challenging rational exponents, like rational exponents in the form m over n. That looks like this. If we have any base, and our exponent is now instead of 1 over n, it's another integer over n. Okay, so now any fractional exponent, not just one that has 1 over a value, we can work with. And it's the same principle. The denominator of your exponent defines the root, okay? That is the index of the root. And our base is still under here. But then when we're done, we take that whole thing and we raise it to the power of m. Okay? How does this make sense? Well, you can split up this. We could use our laws. This is kind of off to the side thinking, which we're going to work through with an example. But b to the power of m over n is the same as b to the power of m times 1 over n. Okay? So we're applying the exponent m and we're applying the exponent 1 over n at the same time. Well, the exponent of m can just stay there, and the exponent of 1 over n transfers into the nth root. Okay, if you didn't understand that, that's okay. We're going to see a few examples. Just wanted to kind of break it down and show you what's happening. And now we're going to show what's happening with real numbers as we go to example 2a. Example 2a, we're given 8 to the power of 2 over 3. So you can see we have a rational exponent in the form of m over n. It's 2 over 3. What we're going to do is split this up into two things that we actually understand. So this is the same as, according to the laws of exponents, we can express 2/3. 2/3 is the same as 1/3 times 2. 1/3 times 2. Okay? Can you argue with that? 2 times 1/3 is 2/3. We're all in agreement there? Okay. Now, what law allows us to multiply exponents together? The power of powers law. The power of powers law says that if you have a base to any power and it's raised to another power, you can just multiply those powers together. Well, that's the exact situation we're in. Just one of those powers happens to be a fraction in itself, but look at what happens. This means that we can say 8 to the power of 1/3 to the power of 2. Okay? So this is just using the power of powers law backwards. And now we can take what we know about rational exponents, and this is a nice one now. It's 1 over 3. Well, that's just looking like the cube root of 8, and we still will have our value in the brackets squared. What's the cube root of 8? 2. 2 squared is?
4.
So 8 to the power of 2/3 is 4. What really happened? You took the cube root of it, which came from the denominator, and then you squared it, which came from the numerator. Okay? So it seems like there's a lot going on here. It's actually pretty straightforward, and if you do a bunch of them, you'll get the hang of it. Oh, I take the cube root of 8 and then I square it. Okay? You'll be able to go straight from this step and rewrite things like this, and then you can see we're right down here at the answer. In B, we have 81 to the power of 5 over 4. So again, I know I'm taking the 4th root of 81, and then I'm going to raise it to the power of 5. So this looks like this. 81 to the power of 1/4 to the power of 5, which is the 4th root of 81 to the power of 5. The 4th root of 81 is 3. 3 to the power of 5, I'd probably use my calculator for that, but 3 times 3 times 3 times 3 times 3 is 243. So 81 to the power of 5/4 is 243. Notice that our exponent here is bigger than 1. 5/4 is greater than 1. So our answer ends up being greater than 81. It's nowhere close to 81 squared. 81 squared would be a massive number. Okay? Massive, not massive, but around 1,000 or a little bit less. But 81 to the power of 1.25 is really what this is 243, and this is how we do it without a calculator. Okay, so you could get this. I could have a no calculators quiz and put this problem on there, and you would be able to do it as long as you know the laws. Okay, in example 2c, we have a rational base and a rational exponent, and the exponent is negative. What's my first step? Yeah, I want my exponent to be positive, which means I'm going to take the reciprocal of my base. So instead of 49 over 81, I'm going to have 81 over 49, and that will be to the positive 3 over 2. And now I can rewrite it. I've got the square root of my base, which is 81 over 49. And we're going to cube that. The square root of 81 over 49 is the same as the square root of 81 over the square root of 49. I'll write that step. I won't always write that step, and you don't necessarily need to, but for the sake of an example, it's probably good. And now what do we have? The square root of 81 is, and the square root of 49 is 9 over 7 cubed, means 9 over 7 times 9 over 7 times 9 over 7. Multiplying fractions is top times top times top, bottom times bottom times bottom, which means we have 9 cubed over 7 cubed. I'd put both of those in my calculator individually, or you can probably do it in your head if you're careful. We've got 729 over 343. And these examples are an application of this right here. Okay? Working with a rational exponent in the form m over n. Okay, where the first two examples had us practicing new things. Example 3 is just old things, exponent rules, but the exponents are more challenging because they are rational exponents. So it's a bit of a mix of new and old here. The first one says, and when I'm doing these, I'll often draw my line, my division line first. I've got x to the power of 2/3 times x to the power of 2/3 over x to the power of 1/3. Now there's usually a couple of different ways that you can do these things, but when I look at this, I would right away say, I don't really know what I'm going to do. I know my base is x each time, so it's going to reduce to x something, right? X to the power of something, or maybe even just x, I don't know, or maybe x will be in the denominator, however it works out, okay? But I would look at this and say, what can I do? How can I make this look easier? What would you do?
Can you multiply the exponents?
So you're on the right track. It's not a power of powers, but we do have the product of two powers with the same base. So I have x to the power of something times x to the power of something, which means I can keep my base and do what to the exponents?
X to the power of 2/3 to the power of 2.
So whenever you have the product of two powers with the same base, you just add the exponent. So I have 2/3 plus 2/3, which is 4/3. Okay? So the numerator reduces to x to the power of 4/3.
Why isn't it 4?
The denominator can still be to the power of 1/3 because the product law says that when you have the product of powers, you add the exponents. So you have 2/3 factors here and 2/3 factors here, and they're multiplied together. That means you have 4/3 factors of x. Okay, well, now I have a single power in the numerator and a single power in the denominator. And we can make a note that that was product law. Product law, or rule, I guess is the word we're using. Product rule. Now I have a single expression in the numerator, a single power in the denominator, and they both have the same base. So what's my next rule? I have a power being divided by another power. I can subtract the powers, okay? It's called the quotient rule, and it says I can take my numerator, x to the power of 4/3 minus 1/3. 4/3 minus 1/3 leaves me with 3/3. 3/3 is 1. X to the power of 1 is just 1. What happened here? This was the quotient rule. And then here all we did was simplify.
Or to just get 1.
I have a question.
Not 1, x.
X.
To get x, to simplify the expression using exponent rules. Okay, folks, you could have also done this in one step. So if I see this You could also just take your base. You have 2/3 plus 2/3 minus 1/3. Okay? You end up with 4/3 minus 1/3. That's 3/3. That's x. Okay, so you could do it all in one step as long as you work left to right, top to bottom kind of thing. Okay, and don't mix up your laws and rules.
Oh, that's easy.
That's fine.
Okay, here's our next one, and you can look at it. You notice you have a base y in both of these pieces, and they are powers raised to another power. So we're looking at the power of powers rule. So the first thing I would do is simplify each individually. So you've got y to the power of 1/4 times 2, which is 2/4 or 1/2. And then our next piece is y to the power of negative 2/3, because that is 2 times negative 1/3.
Oh,
Okay.
yeah, nice.
Now, there are two different ways you could do this. You could, I mean, you wouldn't do this, but you might think, oh, I know what this is. This is the square root of y, so I'll write that. And oh, I know what this is. This is the cube root of y squared, except it's not really because there's a negative sign there. So what you would actually do is you would say, I have a power with a base y times a power with a base y, which means I can add my exponents. So now you're in a spot where you're going to add your exponents, but you have 1/2 plus negative 2/3. Can I add halves and thirds? I need a common denominator, okay? So here's what we're going to do. I'm going to do it. I know what my goal is, okay? And actually I'll do it different. I'll rewrite what we're going to do. We have a product law, so I'm going to add negative 2/3 in the exponent. And now I know that I'm just thinking about my exponents over here. And if I even wanted to, I could take this work off to the side. But I need a common denominator. What's a common denominator between 2 and 3? It's going to be 6. So I'm looking at y to the power of 3/6 minus 4/6. Which gets me y to the power of negative 1/6. And now I think, okay, I have a negative exponent. That flips it into the denominator. So I have 1 over y to the power of 1/6. And y to the power of 1/6 is the 6th root of y. This is a good enough final answer, okay, as it is. But you could also write it like this. Doesn't really help you, but these are the same expressions. Okay, the last one's a little bit trickier. I can see here in our first group, first piece, I have a power of powers, but this exponent of 2 applies to the variable term, variable piece of the term, and the numerical part of the term, okay? So the first thing I want to do here is I'm going to just kind of distribute it using my power of powers law. I have 5 squared, which is 25, and I have x to the power of 1/2 to the power of 2. Well, that's x to the power of 1, which is just x. And then my next piece, I have 4 to the power of x, sorry, 4 times x to the power of negative 1/2. So here it looks a little bit tricky. First of all, this negative 1/2 only applies to the x, not the 4, because this is not in brackets, okay? And then you might not be sure what to do because you have this 25x, he looks pretty good, and then you have this different thing over here. But what's true about multiplication? Actually, maybe say it this way. How are these guys joined?
Multiplication.
This is multiplication. How are these guys joined? Multiplication. How are these guys joined?
Just divide.
And multiplication is commutative, which means I can rewrite these in any order I want. So I can deal with my numerical pieces together, and I can deal with my x's together. So what I actually have here is 25 times 4, which is 100, times x to the power of negative 1/2. Well, if I'm multiplying x times x to the power of negative 1/2, this is x to the power of 1, which means I can just add my exponents, which gives me x to the power of positive 1/2. Okay, so again, it looked pretty ugly, we're remembering a couple of properties, the power law, power of powers, and then the product law, and the idea that multiplication is commutative. We can multiply like, I won't call them like terms, but you can multiply the numerical parts together and your variable parts together as long as the base is the same, right? Okay, example 4, we're going to solve a real-world-ish problem that involves rational exponents. We're given a formula, and it says the following formula relates the volume and surface area of a sphere. Okay, so if you're thinking about a giant ball, as the surface area grows, as the material used to make the ball grows, or you use more material, it can obviously contain more, so the volume will grow as well. Does that make sense? So we are given the formula that the volume of the sphere with respect to the surface area. So as the surface area grows, the volume will grow. As the surface area shrinks, the volume will shrink. The relationship here is given by, in the numerator, 4 pi, right, to the power of negative 1/2 over 3 times s to the power of 3/2. And we need to find the volume to the nearest cubic meter of a spherical holding tank with a surface area of 100 meters squared. So we're looking for surface area of 100 meters squared. Okay. What are we going to do? Well, if we know the surface area that we're aiming for is 100, then we can just look for V of 100. Okay, the surface area is going to be 100, so we're looking for the volume of the sphere when surface area is 100, and it is given according to this formula. There's nothing in the first part that contains a variable, so I'll just copy that down. Second part has a variable, it's 100 to the power of 3/2. So all I did was sub in 100 for s. Okay? Now we can simplify parts of this. This part up here, I would use a calculator to do. Okay? That ends up being, in the numerator, 0.282 if you punch it in properly, over 3. But this part, we can do this. This is, if I wanted to rewrite it, you could come over here and rewrite that piece of it. 100 to the power of 3/2 is equal to the square root of 100 cubed. Okay? Take this, this becomes the index on the radical. 100 is the radicand, and then it's raised to the power of 3 on the outside. Square root of 100 is?
10.
10 to the power of 3 is? Sorry, 1,000, not 10,000. Yeah, 3 zeros. Okay, so I can plug that back in here. 1,000, right? And now I use my calculator in whatever order I want. I go 0.282 divided by 3, enter, times 100, enter.
1,000.
Times 1,000, thanks. Which equals 94. So the volume of this holding tank is approximately 94 meters m squared, m cubed, m to the power of 4, what? Volume. Volume. Okay, volume is cubed. The surface area is 100 meters squared, right? Volume is always cubed.
Were you telling me when we did
Practice problems that you should be able to do come from page 175,
we did all this
numbers 1 through 6.